All right. What is common mode feedback circuit? Even though that is the bottleneck usually for op-amp design, especially for fully differential op-amp design. However, don't be afraid of that because the major reason is you are not familiar with that. Not because it is really complicated, no. Yeah, after I explain the concept, then for the detailed circuit, I don't think most of you will be scared. No, the concept actually is good enough. Then the circuit itself, I don't think it is complicated. All right. The major purpose again is to keep the two outputs, the common modes of your output at a constant level. And I told you already, usually halfway between your VDD and the VSS to maximize the output swing. That's it. Okay. Yeah. When necessary, we will use capacitor, but to stabilize the operation. But it will also slow down the response. Okay. Yeah. To prevent oscillation, it means to stabilize the overall circuit. All right. Yeah. Anyway, simply because you are not familiar, not because they are really complicated. No. No. Okay. Yeah. And again, where to apply your CMFV input to the end, so to the other side. Okay, and those two are for current director. If you cancel it, then you need to flip it up to be the regular case code. That's it. Okay. Anyway, anyhow, quite easy to understand, right? Okay, this is the first circuit I would like to tell you. We call it continuous time. It means static CMFV circuit. Anyway, yeah. Why we call it continuous time? Because the DC current, IQ, okay, flows all the time, never be stopped. So for such kind of continuous common mode feedback circuit, usually it is power wasting. You waste some power to make it. All right. Okay, let's go for it. What is this? VCMO. It means the ideal common mode voltage for your output. Okay, and again, usually, see, 50% of your VDD and your VCC or VSS. Okay, and how it works? I told you already. The real output, if the common mode voltage becomes higher, then you need to also becomes higher. You need to track the output, the average of your output voltages. Okay, so let's see how it works. Yeah, easy to understand. Actually, if you see, see, if this one becomes higher, that one also becomes higher, right? And this is some kind of P differential cell, differential input or pair, right? For such kind of P differential pair, if it becomes higher, VGS becomes smaller, right? And for all those, they provide DC current, right? The same current flows down, but you get less. It means I get more. That's it. That's it. I get more, and also this. Okay, because again, this is higher, smaller, then larger. It means most of the current will flow from here to there. So this is diode connected. The higher current means what? The higher voltage, right? Right. Because it is VT plus delta V, and delta V proportional to the square root of I. If I is fixed, then it is proportional to this, right? But right now I is not fixed, so it is proportional to the square root of the current flows in. That's it. So the higher output, the higher CMFV output. Bingo, that's it. The only problem is you waste static power. That's it. Let's go to the other circuit. static too. Yeah, I only show you the simplest one. If you would like, you can go further for more complicated one with better performance but harder to. Okay. All right. You can see if it is increased, it is increased. According to this is PMOS, so 1 VT, 1 delta V higher, right? So if you increase the output, this node and that node will also be increased. And then this is MOS. Oh, that is also a very simple but good idea for you to know. Okay, later I will explain. Okay, this gate voltage is increased. How about the trend? How about the source? The same, right? Because 1 VT, 1 delta V. That's it. Bingo. So that is some kind of trend, a trend reaction. 连锁反应. Okay. Trend. Yeah. 1 VT, 1 delta V higher. 1 VT, 1 delta V low. So this voltage and that voltage should be linked, should be coupled strongly, right? The higher here, the higher there, the lower here, the lower there. Congratulations, that's it. Bingo. Okay. But I would like to learn more. This and that. A very good idea for you to couple the node voltages. Again, here to there, 1 VT plus 1 delta V. And then 1 VT, 1 delta V lower. In theory, this node voltage and that node voltage should be exactly the same. Right? Right? In practice, because this is a VTP, that is VTN, they are not the same. And also the delta V here and the delta V there, they are not the same. But you can try your very best to make them about the same. Bingo. Keep this in mind in the future. If you face some kind of challenge, how to lock the node voltage to the other? Okay, this is a very simple but a good idea. Okay, that's it. But you need to be careful because to make the circuit functional, you need to apply bias. You need to apply bias. Okay, without the bias, they simply cut off. Nothing will happen. Okay, that's it. Wow. So bias here, bias there, right? And M1 and M2, the bias is provided by M5. Okay. Again, easy to understand but power consuming. Let's go for the other power saving CMFV circuit. Usually it needs to be dynamic. All right, instead of static, just like this. Dynamic usually needs the help of, again, SC, switched capacitor. This is a very important idea, switched capacitor. Okay, even for ADC deck design, blah, 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 sometimes we need SC for help. Okay, what is the concept? That is the real, in theory, we need V bias 4 and common mode output voltage. Okay, if you go back. Here. You can see V bias 1, V bias 2, V bias 3. All that is the ideal V bias 4. Okay? But right now we don't connect V bias 4 all the way to that. Why? According to process variation. Okay? That's it. So if nothing wrong, V out and V out plus V out minus, they need to become VCMO. Okay, I mean for DC operation without any input, with the same input as you like. All right, and then V bias 1, 2, 3, 4. But after fabrication, this one will be changed, right? And then we need to change the bias for M11 and M12. And this is the reason why you cannot connect them to V bias 4. But anyway, in practice, the voltage difference between your VCMO and the V bias 4 should be the same. Okay, should be kept the same. Should be kept the same. So this is a concept. This is the ideal value for your output common mode voltage. Ideal value for the bottom. Okay, for the bottom transistors. And then V out plus, V out minus. They are what? Real output voltage. This is ideal, and this is real, and real. That's it. Ideal and ideal. Okay? So what you can guess? From the beginning, we have two phases. Phi 1 and Phi 2. They are non-overlapped. 它们不重叠. So first of all, we close Phi 1 to sample the voltage at the ideal voltage difference between VCM and V bias 4 stored on C2. Supposed to be C2 and C1 are the same. They can be different, but usually we design they of the same capacitance. Okay, from the beginning, no charges inside, so all the capacitors have zero voltages. But when Phi 1 are closed, C1 was charged to VCM minus V bias 4, delta V, okay? The voltage difference you would like to have. And then, for the second phase, we open it, then close Phi 2. But Phi 2 is 0, right? So what is the consequence? If C1 and C2 are the same, then for the first cycle, C2 will become delta V by 2, right? And how about the second cycle? The first phase, close it, you become delta V. But after Phi 2 are closed, you are delta V, I am delta V by 2. So what will be the consequence? I will become, right? So how about the next? 7 by 8, 15 by 16. Anyway, anyhow, the voltage arrow, I mean, you are delta V, I hope I am also delta V, right? Right? So for each operation, for each cycle operation, the voltage arrow, I mean, this is what we need to have, delta V. But from the beginning, you have only 0. So the arrow is delta V. For the first cycle, the arrow is reduced by 50%. Delta V by 2. Okay? For the next cycle, it is also reduced by 2. So the arrow will become delta V by 4. For the third, delta V by 8. I mean the arrow. Okay? So it looks like SAR, successive approximation. 逐步逼近，渐进式。Okay, that's it. So after some cycles operation, delta the difference will approach 0 very soon. Okay, that's it. That's it. So what's the consequence? Again, if the real output common mode voltage is higher than the ideal one, VCMFE will also, with the same amount, higher than the ideal one. I follow your step. Bingo. Easy to understand, right? So after stabilization, you can see, the arrow is reduced almost to 0. It means what? Delta V on C2 and also delta V on C1. So never mind you close Phi 1 or you close Phi 2. No more charge redistribution. They are already the same. Okay. So it means what? Almost you don't need to waste any power. Okay? And this is the reason why we call it dynamic. No static power is required. It is good. But usually, it is harder to understand for new designers. But anyway, through my teaching, through my help, anybody in the class have any misunderstanding? Raise your hand. I hope everybody in the class know exactly the idea. Okay, piece of cake, right? So easy to understand, but that is the so-called bottleneck. Is it difficult? No. No. Hopefully, through my help, it becomes much easier to understand than before. Okay? Anyway, this is power saving, but area wasting because capacitor is required. Okay, that's it. Yeah. If you would like to enhance not only the gain but also enlarge the output swing, then we need to apply such kind of gain boosted cascode. So this is 1/4, then counterpart, left half, right half, in the middle. And also we apply folded input. That's it. Okay, again, without folded, for the input, you just remove the current redirector. 电流导向器拿掉. Then this one needs to flip back to the top. That is the original structure. But with original structure, the operation range will be reduced. That's it. Okay? And here is some kind of performance comparison for the traditional op-amps. This table actually is from Allen's textbook. All right, believe it or not, I don't care. That's only for your reference. Anyway, according to Allen's telescopic, good at no. Who provided you the most gain? Oh, gain boosted or 2 stages. Okay, blah blah blah. Yeah, but how about the operation speed? The higher gain usually means the lower operation speed. Okay, the smaller bandwidth, blah blah blah. Okay, for your reference. Anyway, I told you already. From the beginning, you need to select one structure to fit your application instead of create a new one. No, forget about it. Even though I teach you already how to create a new one in a systematic way, but my recommendation is never use it. Okay, never apply such kind of systematic way to invent a new one with more than 100%, with about 100%. Your new op-amp won't be functional. Okay, forget about it. Yeah, unless you are Einstein in this field. I mean, in analog IC design. Otherwise, don't touch the new structure. Only select a proper one according to the gain, the output swing, the speed, the power, the noise. Okay, yeah, select one. Good enough. Then do some kind of modification. If you are not happy, even we apply to the final, we apply not only cascade but also gain boosted. That is to enhance the gain. And how about folded? To enlarge the output swing, to enlarge the operation range. Okay, don't get any kind of misunderstanding. Folded is not for gain boosting. No, that is for operation range enhancement, enlargement. Okay, yeah, but for gain boosting, gain boosted, cascade, yeah, those are good for gain boosting to enhance the gain. Right? If you are not happy, then we can go further. Other basic gain enhancement approaches. Yeah, the easiest way is cascading. Okay, that is not cascade. Cascading means one follow the others. They are connected in series. And how about cascade? I am here. On top of me, it's you. Okay? Okay? So the concept for cascading and cascading are totally different. All right? For example, what is cascading? My output to your input. This is cascading. My output to your input. Okay? But for cascading, you are on top of me. That's it. Yeah, 一个叫串接，另外这个叫叠接，叠在一起。Anyway. Yeah. Ideally, if A1 Not good enough. Then we apply the second stage. Oh, not good enough. Oh, blah, blah, blah. In theory, the gain is the product. I mean, is the multiplication of all of them. Oh, congratulations. But I need to warn you. I told you already. Usually, we have such kind of high gain amplifier for what? To put in some kind of negative feedback loop, right? To stabilize the operation. Okay? Then something will go wrong. Yeah. From the past till now, it proves that for more than 2 stages, I cannot say it is impossible, but I need to warn you. It is really, really hard to stabilize the overall negative feedback circuit. Okay? Okay? Yeah, I mean, you put this cascading amplifier into the negative feedback of your application. I need to warn you. For more than 2 stages, usually you will create one pole in right half plane. Right half plane means what? Means what? Unstable. Unstable application. I don't think you like it. Unless for oscillation. You need some kind of oscillator to provide reference clock. Unless for that. Otherwise, I don't think anybody would like to have such kind of right half plane pole. Okay? Till now, from the history, very few cases are successful. I mean, in feedback loop with more than 3 stages. Okay? The key word is, oh no, the key words are more than 2. And then, in closed loop application, next feedback loop. Okay? So, it means what? If for open loop, as you like. Again, don't get any kind of misunderstanding. If this is for open loop, then as you like. No stability concern. Only if this one, and that one, they are stable. Then for such kind of cascading, for open loop application, I mean, you don't connect your output through some kind of feedback network back to your input. Well, good enough. For such kind of open loop applications, you don't need to care about this. Okay? Maybe you will be curious. What kind of open loop application for such kind of high gain amplifier? Comparator. 比较器. Voltage comparator. Okay? For ADC, you need to compare your input voltage higher than this quantization level or that quantization level. Above it or lower it, okay, you need the comparator. For such kind of case, you, especially for high accuracy one, you need high gain comparator. Don't be scared. Wow, usually three stages, but don't challenge me. Hey, look, teach us. Not more than 2. Oh, sorry, this is for closed loop, not for open loop. Okay, for open loop, it is still possible. Okay? Yeah, anyway, that is what I would like to tell you. So, very limited success from the past till now to stabilize more than 2 stages in negative feedback loop. Okay? And this is the reason why till now, for high gain amplifier, humankind only focus on 2-stage amplifier. The differential input, never mind the gain boosted cascade, I don't care, I don't mind. And then the second high gain stage, no more than that. Okay? If you have the 3rd stage, not for voltage gain, that is for current gain. To enlarge your driving current, your output current. Okay? Then we focus on such kind of 2-stage op amp. That is the very fundamental one. You learn already from microelectronics, so I wouldn't like to waste your time. I only have very brief introduction. The first stage is differential amplifier. The second stage is what? Common source. That's it. Okay, but usually it's maybe 100 here and 10 there. So totally 1,000. More likely it will become unstable. So we need compensation. Okay, that's it. And how? Oh, don't ask me because you learned already from the microelectronics. Just read by yourself. All right. And then, how about this structure? The same. But for negative, for the feedback, we have not only capacitor, but this one. This is what? The so-called transmission gate. But it is turned on, right? You are the NMOS connected to VDD, PMOS connected, so both are on. For what? To emulate resistor, 模仿电阻. That's it. So, in theory, it behaves like a resistor. And for what? We call it zero nulling resistor. Yeah, to help you get more phase margin. Blah, blah. What? Yeah, just do it by yourself. Okay? Because again, that's kind of very brilliant idea. I mean, with the resistor to cancel 1, 0, right? Yeah, to the right-hand plane, to my memory, okay? Anyway, humankind created more than 40 years ago. Don't ask me how to derive it. More than 40 years ago, very old. We are modern humankind. We only focus on technologies even more advanced than this. Okay? But in this way, you can see, wow! Congratulations! The gain is around 10,000. Hey, guys, look! 40 years ago, humankind with very bad process, they can achieve more than 10,000 huh? In gain. How about you? 100,000. Hopefully. and you can see the phase margin is 70. Okay? Through the help of this resistor, otherwise they cannot make it. So this is also a very important idea for you. Okay? Yeah, anyhow. And then we have such kind of transconductance amplifier. Yeah, it means the output will be current instead of voltage for some reason, for some application. Okay, how to make it? This is a differential input, but you can see that is original one. All right. So the idea is, again, more than 35 years ago, or very old, right? We convert the input voltage into output current. Then we apply current mirror to enlarge the output current. Okay, so 1 to K. K much larger than 1. That's it. And you can see, if you only need one-sided, yeah, single-ended output, then 1 to K, then M7, M9, 1 to 1, right? So the current will be duplicated here with different direction configurations. They will be summed up to the output. So the output current will be doubled. Okay? It means the output current gain will also be doubled. Right, that's it. Piece of cake. But it's not so good for current gain. Why? Because even though GM is large enough here, but after that, only multiply by K. To make enough current gain, K needs to be very large. It doesn't make any sense. So allow me to show you another better idea. Modified OTA. What is the major difference? Huh? Again, use your eyes as cameras. Have a screenshot. Then go back to the original one, right? What is the major difference? M7. What is M7? Oh, yeah. Here. M2 and M3. See? From the original one, they are diode connected. It means what? They provide no voltage gain, right? Because diode connected means the gain is really small because the output resistance is really bad, really small. Okay. Anyway, anyhow, see here, no diode connection. So it means again, input voltage converted by M1, M2 into output current. But with M3, M4, DC bias, DC current, it means the resistance is much higher than before, right? So we can enhance the output voltage here, right? Input voltage into output current. Our output current through the help of M3 and M4 into output voltage. And this output voltage, and again, amplified by M3 and M4, right? To be output current, then the same. Okay? So, M3 and M4 help to enlarge the first stage output voltage gain. And at the same time, enhance the output current for the final stage. That's it. Okay? So with such kind of modification, a very small modification here, you can get much higher gain and also better frequency response. That's it. Okay. Yeah. For current output, usually we hope the output resistance is really high to push all the output current to the load, right? If you have this requirement, then you can apply cascade. That's it. To enlarge the output resistance, if you look at from your load, look back from your load into your output stage, right? That's it. Okay. But usually we don't apply this. Usually we are happy because the load look like this, right? For AC condition, usually this is large enough. It means the impedance is small enough. So we don't need to care about the output resistance. Yeah, that's the reason why. Okay? And this is some kind of conclusion, some kind of general performance specification, kind of CMOS two-stage op-amp, the open loop gain, 3 or 4 order enhancement, CMR 60 to 80, PSR 6 to 80, right? Yeah, input offset, yeah, again and again. Yeah, usually 2 to 5 millivolts. This is, please pay this attention, okay? 2 to 5 by 4 order. It means the output, the DC output voltage is saturated already. Okay, so you must be very, very careful. To be honest, for high-end application, the most difficult, the most you got to face input of. If the gain is not good enough, then we have many kind of tools, weapons, skills to enhance your gain. But how about input offset voltage? It's really hard to deal with. Okay, especially under high gain application. Wow, the impact will be also enlarged. All right, and how about blah, blah, blah. Okay, just for your reference. Okay, yeah. Yeah, anyway, how about this? All for design optimization, automatic optimization. Okay, forget about it. Yeah. I told you already, usually we don't have the chance to do such kind of automatic optimization. You are your own machine to do all the dirty work. So you need to train yourself as experienced as possible. Okay? Then, here, what is the challenge you need to face with new processes? 20 nanometer, 7 to 5. Wow, a lot of bad issues happens for analog IC designer. Okay? Yeah, but before that, how to enhance it? I gain boosted. I told you already. Okay. Wow. Folded. I told you already. Anyway, and the other one is they apply cascode and cascade. Cascode here. I told you already the difference. The output is connected to the input of the second stage, and this is only the quarter circuit, right? A counterpart circuit, half circuit. Finally, you get this two-stage cascode and cascade amplifier. Yeah, it is created recently. Instead of 30 or 40 years ago, less than 20 years ago, only 18 years ago, good enough, new enough. Okay, but they applied similar ideas, cascode, cascade. Anyway, okay. Anyway, that is more difficult for analog IC designer to face. Yeah. For all those existing approaches I told you, or I didn't told you. Anyway, there are some kind of difficulties. For example, if you have such kind of open loop amplifier, you can design a very high gain, but they are highly process dependent. And also, we hope the linearity and the accuracy, okay, should be good. But with new processes, they are simply unacceptable. They have much non-linearity. They have much worse process variation. Okay, then we put the open loop amplifier into the feedback amplifier, right? Yeah, to control the stability, we need a good match for your feedback network. Okay, that is a piece of cake. But again, we need very high gain. But I told you already, with new processes, the GM is reduced according to early saturation. And the GO is increased according to leakage. Because the gate oxide becomes thinner and thinner, right? It is not isolated anymore from your channel. It is leaking. 它会漏电. Leaking means more conductivity, or it means RO is reduced substantially. So it's really bad. Yeah. Okay. So what we hope is to improve the linearity, the accuracy in open loop amplifier, and to get high gain in closed loop amplifier. But it's really hard with new processes. Okay. Yeah. Till now, very few successful cases were found on Earth, yeah, to improve the linearity and accuracy with new processes. Really, really hard. Okay? And how about to get enough high gain for closed loop application? I told you already, GMGO means much worse than before, right? So, and also the supply voltage becomes really low, really smaller than before. So some kind of fundamental limitation you need to face. For example, cascode, maybe you cannot apply anymore. Okay? But the RO right now is no good. Anyway, you cannot apply cascode. How can you enhance your output resistance? It's really troublesome. Yeah, because VDD is too low. No cascoding. So it means RO is supposed to be very low than before. How can I enhance you again? The only way is GM. But GM means the W over L needs to be sky high, sky large, very large. It wastes your power and chip area. It's really expensive. So anyway, to be honest, till now, no major breakthrough. So anyway, how about cascading? No good for new process because only 2. No more than 2. Otherwise, you will get unstable situation. How about cascading? Sorry, no good for low supply voltage. Cascade, forget about it. Gain boosting, cascade, no. Okay, so maybe only one way out. It is negative impedance compensation. In brief, positive feedback. Okay, so allow me some more minutes. I had better finish it in this week. So that is the second brainwashing for you guys in this class. I would like to help you more. Yeah, through the help of Professor Geiger. Ask yourself, what kind of stability required for your design? So first of all, from microelectronics all the way to all the text, all the Bibles for analog IC design, they always, not usually, they always teach you, you need to design a stable op-amp. So we even apply minor compensation to stabilize your op-amp. Then we apply such kind of stable op-amp to get a stable application. Okay, but what is the difference between op-amp and your application? Usually, again, we put op-amp into some kind of negative feedback loop for your application, blah, blah, blah. So ask yourself, do you really need a stable op-amp? Maybe not, right? Because the final purpose is to get a stable op-amp application. The application needs to be stable, otherwise you will oscillate. It doesn't make any sense. So definitely, this, in theory, this is yes, and that is no. Right? In theory, do you need a stable op-amp to get a stable application? No. But you will be curious, how about in practice? Because usually people teach, or not always, they teach you, you need a stable op-amp to get a stable application. Okay? Yeah, I will show you some kind of good examples to wash your brains. So this is the major question. Does a stable application require a stable op-amp? Hopefully, the answer is no. Okay, so allow me to show you a very old filter circuit. Okay, that is a bridge T biquad. If you are curious, just Google online. You will see what's that. In the past, 30 or 40 years ago, for telecommunication. Okay. Anyway, with such kind of structure, this one should be unstable. How? I show you the original. That is very popular in 70s. Right now, it's already almost 2020, so around 50 years ago. Okay. Yeah. Anyway, this is the realization of such kind of telecommunication circuit. Please look at this. It is positive feedback. Okay? If you analyze the circuit here, the amplifier here, it is unstable. But put into the loop, it becomes very popular in 1970s. Okay? If you are curious, hey, my teacher told me never design such kind of unstable circuit. So you would like to change for safe reason, to play safe, 安全起见. Okay, you make it. The feedback needs to go back to the inverting amplifier and this become positive, right? That is what you were taught in the past. So you say, hey, look, professor, it is incorrect. You have the wrong signs for positive and the negative input. Okay. Yeah. After you change it, no good, right? You swap it. Okay? Anyway, to make it become stable for the amplifier, but you put this stable amplifier back to the original circuit. Unluckily enough, the total circuit become unstable. Are you happy? No. No. Okay, so what's the lessons you learn here? With such kind of positive feedback amplifier, unstable amplifier, for the whole circuit, it is stable. If you make it stable, then the whole circuit will become unstable. That is the lesson you need to learn from the past. 50 years ago. 50 years ago. Okay? We are modern humankind. We need to learn more. We need to go further. Okay? So, lesson 1. You can see, with stable amplifier, you get unstable filter. Instead, with unstable amplifier, you get stable filter. So it means what? The stability of the overall application, I mean of the closed loop, of the feedback network, is not determined by the stability of your amplifier. No. But to be honest, I need to tell you, usually the stable amplifier, usually the application is composed of stable amplifier. That is the usual case. But for some cases, the stable amplifier is composed of unstable amplifier. Keep this in mind. This is what I would like to wash your brain. For the other, even you may say, hey, look, I'm not any kind of telecommunication circuit designer. That is too far away. I would not like to have that. Okay. Let's show me a very easy to understand. You learn already. Okay, for example, this is what? A very simple negative amplifier, inverting amplifier, right? Apply such kind of negative feedback. See, that is what you learned already from microelectronics. A very simple idea. Okay? And usually you think, the op-amp is stable. We call it a dominant power approximation. Because if you look at the frequency response, it look like this and go down, then okay? If we neglect the rest, they are too far away. If we focus on the band we are interested, 如果我们只聚焦在我们有兴趣的那个频带 we can find, if you forget, it looks much similar to only one pole in frequency response. This is the so-called dominant power approximation. We learned already from microelectronics. Okay? So it means, the circuit can be simplified with a single pole. Okay, that is the usual case. Yeah, and then you can see if the single pole is unstable, right? Where is the pole? You set this term becomes 0, then S becomes P. It is to the right plane, right? It means what? Unstable, right? Be brave. Let's go for. This one is unstable, but we put unstable op-amp in such kind of negative feedback circuit. So after analysis, finally, the feedback, the overall gain for the feedback circuit, it looks like this. What does it mean? Again, where is the pole for the overall circuit? We again set it, becomes 0. If beta A0 larger than 1, this is positive, that is positive. Congratulations! The final result is minus P blah blah blah. Beta A0. Positive, minus. Congratulations. The overall circuit, the pole of the overall circuit actually is to the left. It is stable. Right? With such kind of very simple idea you learned already from the past, even though this is unstable, I mean the single pole is to the right half plane, but for this overall application, it is possible to get a left half plane pole to stabilize the overall application. That is what you need to learn. Okay? So anyway, do you need a stable op-amp? No. Do you need a stable op-amp application? Sure, that is the final result you need to get. But what is the question here? Does a stable application requires a stable op-amp? No. So it means what? You can design an unstable op-amp. And hopefully after you apply the unstable op-amp into your application circuit with negative feedback, we can stabilize it again. Allow me to point out that for, I think, all of you, before this moment, before this class, everybody was told to design a stable op-amp for a stable application circuit. No. Please change your mind. And Professor Geiger would like to open your future, to make it much wider than all the other students. They don't attend our classes. Okay? Hopefully that is what we can help. Again, me and Professor Geiger, we never derive any equations, for our students. But we try our very best to explain all the important ideas, to enhance your future. So it means what? Right now, we help you open another door. What kind of door? Unstable op-amp with positive feedback. Okay, I need to highlight again. For the op-amp design, you can apply positive feedback to make it unstable. But what is positive feedback? What is the slogan? You can enhance your gain, but worsen all parameters. Okay? And what I told you from the beginning, what is required for op-amp? I told you already, very high gain. Right? And forget about the others, because we can sacrifice such kind of very high gain into the closed feedback network to enhance all the parameters, all the other parameters. So again, the only requirement for op-amp is high gain. But right now, our difficulty is with new processes, we cannot achieve any high enough gain. All right? Professor Geiger helped to open the door. No worries. Through positive feedback instead of negative feedback, we can design high enough gain for our op-amp, but it is unstable. Never mind. Unstable amplifier can still make stable application. That is the most important idea in today's class. Okay? Convince yourself. You can go further. Be brave. All right? And in next week, never mind how hard I try. I only make it for 200 pages. Maybe I need 1 more hour to finish it. Okay, in next week. So 2 weeks later, don't come here. Go to the computer room for your second homework. And then in May 20-something, I was invited by Boston University of Technology on behalf of our president to celebrate their century event, 100 years. Okay, anyway, I will disappear for one full week. That is the timing for your third homework. And after that, to the final of this semester, I would like all of you to read some articles about very low power design for reference voltage or for temperature sensors. Okay? I hope. What is the definition for very low? We focus on nanowatt. In the past, we focused on microwatt, but right now, for IoT, microwatt still means too much. We need to substantially cut all the way from micro to nano. Okay, but how to make it? Again, I hope you can help yourself and me. Okay, all you guys, two students in one team to read the same paper, and then come here to present your idea. Do your very best to fully understand all the concept. Okay, maybe you don't need to derive the equations, but I hope you can explain in the equation what we can learn, blah, blah, blah. Fine-tune the circuit to get anything we would like to have. Anyway, for voltage, for reference voltage, it should be stable according to temperature. Not only temperature, but also hopefully supply voltage. Never mind what kind of supply voltage, what kind of temperature, you still provide the same output voltage. That is what we want, according to process variation. So PVT, process voltage temperature variation, hopefully they don't cause any harm to your output voltage. That is for the ideal band gap of reference voltage. But to be honest, it's really hard. Okay? And then try your very best to read, to understand the article. Share your understanding to all the students, also myself. Okay? Because right now, one of my team, a big team in my lab, focusing on such kind of very low power design. All right? We can help each other. We can share the concept. So maybe a few weeks later, I will show all the papers for you guys to choose. But right now, you can find your partner. Okay? Yeah. Who will be your team member? Think about it in advance. Okay? A few moments. Positive feedback amplifier. Okay. I will come back this topic. But before ending, I had better show you this. Again, moments ago, I told you if this one is unstable, just like this, P is positive. So the gain of the amplifier, the power of the amplifier is to the right half plane. It is unstable. After feedback, we get this, right? And hopefully, this one is positive. P minus beta GB. Okay? I hope. This is negative. Sorry. It should be negative. Okay? So allow me to show you. See? For the op-amp itself, the power is positive. Okay? This is the vertical axis. So the power is to the right. It is unstable for the op-amp. Okay? But if this one is negative, congratulations. Because the feedback power for the whole circuit is this. So P minus beta GB, if it is negative, then congratulations. The overall circuit has a gain to the left to stabilize the operation. Okay? So what is the possible? Because beta right now is positive. Okay, what is the past? You guys stay here. Everybody warn you, don't close the night. That is too dangerous. If you close the night, you will fall into the hell. Where is the hell? Nobody see it. Okay? So be brave. Close the boundary. Okay, to the right. But don't go too much further. There is another boundary called beta GB. Okay, and what is beta GB? You can go back to here. Okay, just do it by yourself. Here, if you don't cross over the boundary, the second boundary, then P is less than beta GB, right? What does it mean? You can live happily in this region. That is the new territory Professor Guy will help you to open. Okay? From microelectronics to Allen's Bible to Razavi's Bible, they never touch this land. They only, all of them only focus on this. Be brave. Cross the boundary to here. Okay, but not there. So, what is the consequence? You can see for op-amp itself, stable, unstable. But for overall closed-loop application, stable, unstable. This is the new territory. 新的处女地. You can see unstable op-amp, but stable negative feedback circuit, the overall circuit. Okay? Be brave. Yeah. Before I close it, there is something related to this. Yeah, for such kind of positive feedback amplifier, positive feedback means the gain can be increased substantially. Okay, but the parameters all the other parameters of the open loop amplifier will be degraded. Who cares? Because we only need to get enough high enough gain. Okay? Yeah, anyway, this is what I would like to tell you. In the past, you only design this, you only design that. But right now, I tell you, you can cross the boundary to the right, but not too much, okay? So P3 here, P4 there. All of them are positive power for your op-amp, not for the overall circuit, okay? And we would like to simulate the settling time. Allow me to show you. In the past, you have only P1. You only design P1 and P2 for your op-amp, right? The two negative power to stabilize your op-amp, it means the longer settling time. Okay? If you are brave, push the power close to the boundary. You can see, you can speed up the settling time, right? P1 here, P2 there, right? The settling time is reduced. But why in the past we don't design the power very close to the boundary? Because according to process variation, engineers were scared. After some kind of process variation, P2 will cross the boundary to make the op-amp become unstable. But who cares? We don't. Right now, we don't. We are not scared. Okay, allow me to show you P3. Wow, fantastic. What is the settling time for P3? Even smaller than P2. Only if you are brave enough. A little bit to the right help plan, but not too far away. I mean, this is not too far away from the boundary. You can see, not only you can enhance the gain, because this is positive feedback, the gain will be boosted. And also, the settling time will be enhanced. Bingo. Okay? That is a rare case. You can enhance your gain and settling time and speed again. Both. Okay? 这是非常难得哦。你若勇敢的把你的 op-amp 的 power 从左半平面推稍微过右半平面一点点，你不仅可以提高增益，因为它是正反馈 ，OK， 你也可以同时提高它的速度，非常非常难得 ，OK， yeah， again that is a real case you can learn from all those Bibles or not. They never touch it. Okay, but don't push too further. You say, hey, look, in this direction, it's good. From P1 to P2, from P2 to P3, you can see the settling time becomes smaller and smaller. If you push further, see, P4 here. You say, hey, this is shorter. No. It is above the threshold. Okay, so the settling time is much larger than this. Okay, so my recommendation is a little bit larger than 0. I mean, a little bit close to the boundary. Such kind of positive pole can enhance the gain and also speed operation of your op-amp. That's it. But not too much. Okay? Got it? That is the gift I got from Professor Geiger and passed to all you guys here. Hopefully, since after, you have new territory to design. Okay? All the students in the other universities or even in the future, right? They only stay here. But you guys can try to design P3. Okay? Yeah. And your bosses will be amazed. Wow! So good! I am not only talking. I will show you the real result from Professor Geiger's lab. You can read by yourself. Yeah. Not only this. I would like to show you that. Okay. To this brainwashing. Allow me to show you. Okay. Because Professor Geiger found it instead of created. Okay. Oh, a new territory. I mean, a little bit larger than the vertical axis. You can see for such kind of telescopic cascade, traditional one and with positive pole. Okay, so what is the difference? If we go out here, the only difference is in the past we have that. And for positive feedback, we have this kind of connection. Okay, yeah, you will see that such kind of cross again and again for positive feedback. Or we call it negative impedance. Okay, negative impedance. This is less than 0. Okay, anyway, negative impedance or positive feedback, they are about the same thing. So, what is the difference? Not much. Only change this kind of parallel connection will cross over. Okay, and all the others are about the same. Let's check the specification. You will see the gain is increased, right? But how about the others? The frequency the same, the load the same, the phase margin the same, current the same, supply voltage the same. Wow! Without paying anything, no extra cost, only change this to that. You can enhance the gain substantially. Fantastic. Okay, and this is the photo. Professor Geiger has a very good cooperation with TI. Till now, still the best analog IC device supplier. Okay, even the revenue for analog chips from TI is even larger than analog devices, linear technology, than all of them. Okay, Professor Geiger get the real chip, the real layout from TI. This is some kind of ADC. All right, so it only replaced the amplifier. Take out 3 amplifiers, then put the new one. That's it. And go for fabrication. Because it takes a much longer time to design all of them. So forget about it. Because they would like to verify whether or not positive feedback amplifier is possible. Okay? So, after that, they offer 2 chips for blind test. I mean, before sent 2 chips, one is original, the other one is modified. Take out the old, replace the old amplifiers with the new one. Okay, and Professor Geiger told me the new one only occupied 1/3 of the area. The others are open space. Okay, then they get the new chips. So one old, one new cover. Okay, they have something to cover and send 2 chips to TI's lab for verification. RNL, DNL, accuracy, blah, blah, blah. After that, they ask the test engineers, which one is the original? They choose the better performance, the one with better performance. But after they get rid of the cover, oh, it is the new one. Okay? Wow. So after that, TI redo the layout because they are 2/3 are empty. So they can, TI reduce the chip size. But to the market, they still sold the chips with the same price. Oh, TI made much more money than before. Okay, so Professor Geiger told me on the top of the chip, usually there was some kind of marker, 有一些记号, to tell you in which year, in which week of the year the chips are fabricated. Okay, for example, that is maybe 20 something. Okay. Okay. For example, something like this. It means in this year and 26 week, he told me there is a clear cut. In which year, in which week, after that, all the chip with new open design. That's it. Okay, and this is the reason why Professor Guy till now still get a lot of financial support from TI. Yeah, to sponsor his PhD students. For okay, so what did you in today's be brave, right? Everybody, from microelectronics to analog IC design Bibles, everybody tell you it is really dangerous. Don't cross the boundary. We can stay here. Yeah, to play safe. That is good for your future. No. If you believe everything in your textbooks, in the papers, that is really upset for your own future. Don't believe 100% of what they said in the textbooks, in the papers. Be brave. Go to the other side. You will see, oh, nobody can compete with you because you are the new ones here. But right now, you are not the first because Professor Geiger and his students crossed the boundary maybe 15 years ago. You are still late. You are still very late compared to Professor Geiger's team. But right now, you are much earlier than the students out of my class. Okay? So, you are still very lucky. Please, change your own mind. Okay? Again, don't believe in everything. Even don't believe in 100% what I said. Always keep your mind. Always be curious. Oh, is it true or not? Think about it. After thinking, if you think it is true, then accept it. After thinking, if you think it is not true, then discuss with your supervisors, with your teachers, or your bosses. It will be very good for your own future. Thank you. 尽信书不如无书哈，古早人